Hi everyone, good morning. I'm Abu Zair Faridi and I work with Dr. Nirmala Roy in the Mobile Pervasive and Sensor Computing Lab at UMBC. And I'm going to present our paper titled Conditional Domain Embeddings for Scalable Human Activity Recognition. And here's the outline for today's presentation. We start with the motivation for wearable sensor-based human activity recognition. We then discuss the main challenges in this avenue, that is the heterogeneities in the IMU samples affecting classifiers performance. We then give a brief review of the literature on some ways to handle these heterogeneities. One of the simple ways is to provide auxiliary supervision on the heterogeneities, but there are some pitfalls to current approaches. We then provide an overview of our methodology, uh, that is making activity embeddings condition on pre-trained domain embeddings. We then move on to the details of the experiment, pre-processing, and model building, and then we discuss the results and draw our conclusion from those. So, what is the motivation for wearable sensor-based human activity recognition? Well, with the proliferation of low-cost wearable sensors and IoT devices, a large plethora of innovative ML applications are being developed in healthcare, sports analytics, fitness monitoring, entertainment, and skill acquisition training. And the IMU sensors provide an increased flexibility compared to vision and depth sensors, as they allow for a larger action space with unconstrained movements, and they are a little bit more privacy preserving compared to vision-based approaches. But this flexibility comes at a cost, as the distribution of the samples can vary due to the variations in age, sex, dexterity, and training levels of the subjects. So let's take a deeper look into these challenges. As I said in the previous slide, there can be cross-personal heterogeneity, but we can also experience cross-positional and device heterogeneity. For example, you might have a smartphone that you normally keep in your back pocket, and you have been using that to collect and classify your activities for the last few years. But now you got a smart wristwatch and you want to continue classifying your activities without retraining on data collected by the smartwatch. Now, not only you have introduced a positional heterogeneity, but also a device heterogeneity. Because the smartphone and smartwatch might not share the same sensor, and each sensor tends to have its own biases coming from the components and components used and the signal processing employed by the DSP. Now, all these heterogeneities can affect both the marginal distributions and also the conditional distributions. And it actually makes it difficult for a classifier trained on one type of heterogeneity to perform well when tested on another type of heterogeneity. So handling these heterogeneities is important, as the performance of deep learning models relies heavily on the amount and the quality of the labels provided. The traditional approach is to learn the mapping between the data and the labels, right? So that is learning the probability of y given x. But this requires a lot of label samples. Now, there are actually alternatives approaches that try to alleviate the need for a high amount of label samples. We can learn the representation with unsupervised or self-supervised approaches and then train a classifier with a small set of label samples. Or we can adopt a previously trained model to work well with introduced heterogeneities. However, we noticed that in a lot of public data sets, there is an additional metadata information. For example, the position of the sensors being placed in the body, the the device type, or the user demographic. Now, this metadata is often not fully utilized. Um, Most domain adaptation methods actually use this metadata as a domain label, but they are just using it in a very restrictive way. They often handle a single domain heterogeneity at a time or a single source at a time within a heterogeneity. So we asked ourselves whether there is a way to systematically exploit all the metadata information to see if we can improve the classification accuracy. And the intuition is that learning the probability of y given the sample x, the subject, device, and position information would produce more robust models compared to just learning the probability of y given x. So, but before we get into the details of our methodology, let's review some related works on incorporating this type of auxiliary supervision to handle the heterogeneity mixtures. The obvious way would be to use multitask learning. So you would have a common feature extractor, and then we try to classify the domain and the activity labels at the same time with 2 or more classification heads. Now, we can assume two types of relationships between the domain label and the activity label space. It can be globally cooperative, where we assume that the domain classification task will help the activity classification, or it can be globally adversarial, where we assume that the domain classification will degrade the activity classification. So often a gradient reversal is used to make them play well together and learn a domain invariant feature space. But as we will see later, neither of these global assumptions provide better performance than a single task activity classification. But why does that happen? We'll see that later. But we hypothesize that the two tasks are neither globally cooperative or adversarial. The relation should be decided on a per sample basis and should also be learned. So our idea is let the model decide when it knows a sample is coming from the wrist of a female versus a sample coming from the ankle of a male, and then use the information or discard it as long as it increases the final classification accuracy. So this thing being said, let's take a deep dive into our methodology. Our proposed method is called CoDEm, that is activity embeddings conditioned on pre-trained domain embeddings. Our proposed the basic idea is to decouple the feature related to the domains and the activity classification. So have separate feature extractors for domain and activity classification. Features should have geometric embedding characteristics so that similar labels coalesce into close neighborhood and different ones stay apart. Thus, we can learn unique encodings for each domain. And then condition the activity embeddings on the pre-trained domain embeddings. And then finally, train a classifier on the tuned activity embedding. So the next question is, how do we learn the unique embeddings for each domain? We employ a simple contrastive central loss, which allows for minimization of interclass variability and maximization of interclass separability. While there are more sophisticated state-of-the-art mechanisms for achieving the same effect, for the simplicity of exposition, we went with a simpler loss. So with this loss, we first learned the initial activity embeddings, E-act, with the label samples as shown in the picture on the right. After training the embeddings and embedding, each activity gets its unique neighborhood or encoding. Now, the next step is to learn the domain embeddings ED from the unlabeled samples. So with user, position, and device metadata, we can learn user, position, and device embedding vectors z user u, z pose u, and z dev u. And we derive the domain embedding vector zdu by concatenating these three. Now it gets interesting, as we need to find a way to integrate knowledge from the domain embeddings into our activity embeddings. So we want to produce domain-aware activity embedding z hat act L. So we pass the label samples in L through ED to infer the corresponding domain encoding vector ZDL. And then we project ZDL to the same dimension as ZActL with a learnable parameter W and take their dot product to get the attention score. We then multiply ZActL with the attention score to get the updated embedding vector. Now, rather than replacing all the original ZActL with the new set of values, we just add a residual connection so the network can actually automatically choose which features it needs to update. So the whole training process is summarized in this slide. So we use 3 public datasets for our experiments that contain gender and position metadata in addition to having a diverse set of labels. And here are the layer-wise details of the CoDEM's architecture. We utilize depth-wise separable convolution that allows for 7.3 times smaller network size compared to normal convolution. Also, the L2 normalized final projection layer ensures that embeddings are bound in a unit normalized hypersphere, and this alleviates the need for using a scale dot product. We also list the preprocessing and training list details in this slide. During the learning of the embeddings, we need to use a large batch size to have faster convergence for the contrastive central loss. And since we are concerned with the quality of the learned embeddings, in addition to the final classification performance, we use mean silhouette coefficient to assess the quality of the embeddings, and also macro F1 score to assess the final classifier's performance. And then now, the most interesting part, the results. Our first baseline is the normal single task learning, right? Now, the two other baselines are the cooperative and adversarial multitask learning. We can see in the table that ours is the only one that does not require any hyperparameter tuning or can work with a fully disjoint set of labels. And since our focus on this paper is to explore the effect of auxiliary supervision, we deliberately avoid comparison against purely unsupervised frameworks, but the overall ideas present here should be generalizable enough to be adapted into the pipeline of other frameworks. So we are not, this is a complementary idea that we are actually proposing, not like a replacement. So we first try to understand the effect of contrastive center loss in a single task learning setup. As we can see, on average, contrastive center loss provides up to 4.25% macro F1 score and 7.72% silhouette score improvement across the three datasets. This validates our intuition of using contrastive representation learning. Now we add in the cooperative and adversarial multitask learning baseline results. Both the MTL baselines perform poorly compared to the STL baselines, hinting that global cooperative or adversarial MTL models are ill-suited to integrate the auxiliary supervision from the metadata tables. So again, our question is, can a local per sample learned relationship between the activity and domain label space provide a better alternative? And as you can see, CoDEm outperforms all the baselines and achieves an average of 9.5% improvement across the three datasets. And we would like to note that the MTL baselines were trained on samples that contain both the domain and activity labels. And compared to that, CoDEm was trained on samples that contain either the activity or the domain/metadata labels, but not both. So we performed some visual analysis to have an understanding how CoDEm is actually working. We compared the TSNE plot of the single task embedding vector, which is shown on the left, with the domain hour embedding vector shown on the right. And as it is a little difficult to compare all the small data points, we also show the silhouette coefficients. And we can see that there is a high amount of overlap between the samples of 4 activities in figure A. And we can also see that CoDEm actually achieves 11% higher silhouette coefficient. But does the higher silhouette coefficient of embedding lead to a higher F1 score? And interestingly, we can see that a classifier trained on a single task embedding vector confuses these 4 activities again. And on the other hand, the classifier trained on embeddings learned by CoDEm attains 35% higher F1 score on the said classes. And that is where like CoDEm shines. So in conclusion, we built a novel framework to exploit the metadata information to handle multiple heterogeneity with limited label samples. We offered a hyperparameter-free way of learning pre-trainable embeddings from a disjoint set of samples containing either metadata or activity labels. And then we combined contrastive learning with a novel residual attention mechanism to learn the highly compact representation with an average 17.5 improved silhouette score and offer an average of 10% improvement on macro F1 score over 3 baselines in 3 benchmark datasets. And in future, we'd like to conduct cross dataset experimentation, explore some of the potential privacy issues, extend the framework to cover more diverse heterogeneities, and explore the uses of more sophisticated contrastive learning techniques. Thank you all for listening to our talks, and we sincerely thank all of the funding bodies for their continued support. And I'm ready to take questions now.